Well, welcome back to BIOB 105, Intro to Biotechnology. In this chapter, we're going to look at some laboratory skills and talk about some of the things that we're going to be doing in lab in the next week or two. So what we're going to look in this lecture is a look at some laboratory safety, kind of review some of the things that were put into lab archives for the first week, talk a bit about setting up laboratory notebooks, look at types of laboratory equipment, talk about treatment of numerical data, and a bit of lab math and preparing solutions and materials that we'll need in the lab. So it's really important that we understand the hazards and risks in any work environment. And so no matter where you end up working, whether it's in some kind of biotech company or laboratory situation or any work environment, there's going to be some safety training involved. So one of the things I had you do for last week was to look at the FBCC lab safety handout. I put that in lab archives, and I wanted you to read that and understand that. And that's something that we put on that first quiz, was an understanding of those procedures. So one of the things we have to look at is our personal protective equipment. And so that includes our goggles, our gloves, our lab coat, wearing closed-toed shoes, and any other protection that we might need for special circumstances. It might be using a face shield or something like that if we're working with ultraviolet light. And so that's an important part of knowing what to wear in the laboratory. Safety data sheets is something we'll be looking at in lab, and these include information on reactivity with compounds, the flammability, any health hazards. So all the things you really need to know about safety, and also storage of that material. And so these are something that all labs have to keep, and we need to have records of those so that we know all the chemicals we're working with and the potential hazards. In biological labs, and particularly in the biotechnology lab, we talk about biosafety levels, or BSL, and these are based on the potential of the organisms we're working with to cause risk. And so there's a good chart here. It's a little bit hard to read in this slide, so I'll just make it a little bit bigger. So these are divided up into 1, 2, 3, and 4. So BSL1 is our lab, basically. And so we're working with things that are not known to cause disease, or there's very minimal risk. So these are strains of E. coli that we know are perfectly safe, or things like baker's yeast that we'd actually work with in the kitchen at home to ferment or make bread or things like that. So you still do your regular safety that you would in any lab. So you're going to wear a lab coat, and goggles in most circumstances are recommended, and gloves in some cases. But in some cases, you actually could work without gloves. When you get to BSL2, these are things that pose some health hazard. And so many research labs, and certainly clinical labs like the hospital, operate in BSL2. And I think I pointed out in lab the safety cabinets that are laminar flow, and those are the kind of cabinets you work in. So it minimizes exposure of the person, and it also keeps the organism contained in that environment. And so the added things that you would need for BSL2, so everything is the previous level plus more. So we would need to work in those biosafety cabinets, we'd need to wear eye and face protection, and the room that you work in is usually restricted access, so that's another requirement. So BSL2 labs are pretty common in many universities and colleges. We actually could run our lab as a BSL2 lab because we have the equipment. And certainly it's something that's pretty easy to set up. When we get to the higher levels, these are things that take more equipment, and there's a greater risk. So BSL3 are some academic labs, some of the labs that not a typical hospital lab, but maybe a reference lab where we send off samples that might be particularly hazardous. So BSL3 are things that have significant health risk, and there may be limited treatments or prevention. And so these include some of the viruses, and actually the SARS-CoV-2, the virus that's causing our current pandemic, is actually in the BSL3 category. So they need biosafety cabinets, and there's some other personal protective devices. A lot of people do wear complete face shields with that seal completely off their face so that there's no risk of inhalation. BSL4 is the one that's the hardest to achieve, and this is where the person's actually in a complete spacesuit. And so they're very difficult to set up because they need special negative pressure, and there's quite a bit of regulation for those labs. So the closest one to us, there is one in Montana at the NIH labs in Hamilton, Montana, the Rocky Mountain Lab. and they're set up to work with, they can work with Ebola and, many of these very dangerous, particularly viral diseases. So coming back to who sets up the biosafety, so the Centers for Disease Control, the CDC, and the National Institutes of Health are the ones that set up the guidelines for what organisms get categorized in different levels. And I already mentioned we are basically BSL-1 in our lab. And I already mentioned that the SARS-CoV-2 would be a BSL-3 organism. And I think the main reason, even though this can be potentially deadly, we do have some treatments available. And if we moved it to BSL-4, it would be really difficult to do work on it. So they wanted to try to make it more available, I guess, for people to do the research work. And what we can see in the photograph here is this is a typical biosafety cabinet. So this is, like I said, one we do have in our lab. We have a couple of these. So some other safety considerations, some of these are just kind of common sense. We want to take care of any broken glass. So we have a broken glass disposal that's separate from regular trash. If you have any electrical cords, I'm always kind of worried about tripping or getting caught on those and having things come off the cabinets and having exposure. So those are things we take care of. And then we have specific disposal for chemical and biohazard. So in our safety guidelines, I had quite a bit of information about the biohazard disposal. Even though we work with minimally hazardous things, we want to make sure those are everything's disposed of properly. And then chemical disposal, we'll talk about that on a routine basis. Most of the things we work with are fairly innocuous. We really don't have too much worries, but certainly in a chemistry lab, you have things that are more reactive and have separate disposal. If you work in certain kinds of industry, there often are clean rooms, and clean rooms have HEPA filters, which you might have heard of because we have air purifiers and vacuum cleaners with these kind of filters. But HEPA stands for high efficiency particulate filters, and that keeps the air very clean. And when you go into clean rooms, you have to be completely gowned up, even your hair covered, because we have little particles that come off of our skin and that can contaminate the environment. So critical work in manufacturing or testing and so forth requires a clean room with very clean air. So the hazard symbols are things you may have seen other places, and this is something I will put on the exam. I do want you to be aware of what these stand for. Some of them kind of make sense. I mean, I think if you see this little flame here, you recognize that's flammable. You see the skull and crossbones, that's not a good sign, that's toxic. But just be aware that we have different symbols for compressed gases. So for instance, we do have some compressed gas tanks for our CO2 incubators. Those have to be chained up because if they topple over and get dented, they actually become a projectile because of that compressed gas. So something to consider. So general health hazard, you can see there, explosive, that kind of makes sense. Irritants have that exclamation mark. And then oxidizing refers to again, reactivity of that particular material. And then environmental hazard, I think that kind of makes sense what that is. So these are the hazard symbols that are put on specific locations or instruments in the case of the compressed gases or the chemicals that we might be working with. So let's turn our attention to our lab notebook. We are using the digital lab notebook, but I encourage you to keep a bound notebook of things you do in lab, and that way you can just simply scan or photocopy your lab notes to the lab archives. And so this shows you some examples. These are taken from your book, but you can see the elements of the lab entries here with little diagrams or sketches and tables for data. And so if you work on these, if you read the lab, you can kind of see how you want to set up your notebook. And then when you come to lab, you can have the data tables ready to go, and that saves a lot of time. So every lab notebook, it's going to have a title. So in the lab archives, I'm going to have that title there. And when we get to experiments where we have a hypothesis or purpose, you're going to be able to list that. Materials, I will actually have that. You won't have to list that down there. But many times for procedures, I may want you to rewrite that so you understand it, or possibly make a flow chart. And a flow chart kind of summarizes in a little diagram form, like boxes with arrows, the steps in the procedure. So the really important things that we want to then put in our lab notebook would be the results. So what are we observing? So in our pipetting lab, we were doing measurements, and you had those weights and measurements and so forth. And then anything you observe, so like when we did the strawberry DNA extraction, you made observations of what that extraction looked like. So the colors and viscosity and appearance of the DNA that you extracted. Then conclusions would be some specific questions I might ask you, and I'm going to have some post-lab focus questions, but there may be a time when I want you to write a paragraph on what was the overall observation that you made. In addition, after you get these observations, there may also be a data analysis section. And as we move into experiments where there are more steps and more complexity, there will obviously be more analysis to do, and that'll help you get to your conclusions, like what did you really learn from that information. So in your lab notebook, you would write in ink, you would number and date the pages, and there's a write-up actually in the textbook talking about the discovery of Claritin and the importance of dating and actually initialing to show that you did that work, and that sets a legal precedent, and that's the basis for a lot of patents. So it's in a research notebook, that's a really critical step, is to acknowledge that you did that work and you dated it and you set precedents for things down the road. So really important that you record during the lab. When you have a little break, that's a good time to be writing things in your lab notebook. Don't try to count on your memory, because you walk out of lab and then what was it I actually used? So be sure in your results you include your raw data, and then any plots or calculations, the equations you use. So try to be as complete as possible. Then your conclusions will be a brief summary of the things you learned. And then the questions will be follow-up that you might want to, that I will have you answer to kind of help you kind of put together, distill what we've learned in that lab exercise. So a little look here at lab equipment. The lab equipment, we do a lot of liquid measurement. And so if we have large volumes, we might use the graduated cylinders. And so these have measurements. And so the smaller cylinders measure smaller volumes. So these can be anywhere from 20 milliliters up to a liter in size. I've even seen 2-liter graduated cylinders. In chemistry, sometimes you use a volumetric flask, and so there'll be a line right here that will be set for a very specific volume. So if you're going to make up a solution that you want to be very precise, you'll add in the solute, so whatever material you're going to dissolve in the solution, and add the water up to that specific mark. So volumetric flasks are designed for one specific volume, where if you look at graduated cylinders, you could do a range of volumes. Like in a 1-liter cylinder, you could do 800 milliliters, for instance, or 750, we've got a choice. But if you're using a volumetric flask, that's going to be set for one specific volume. Then in lab, we worked with the serological pipettes, which usually are in the range of 1 to 25 milliliters. And then when we worked with the micropipettes, that's below 1 milliliter. And so it goes into tenths and hundreds and even thousands. So it gets into the microliter range. And then we probably won't work with the burettes, but these are used for titration. So you're adding a specific amount of acid or base, and they have applications in specific kinds of measurements, particularly in water chemistry and things like that. So liquid containers include Erlenmeyer flasks and bottles. These reagent bottles can be storing media or solutions that, especially, these are great because you can autoclave them and sterilize them, and I'll talk about that in just a second. So just to kind of a question here, if you wanted to measure 500 milliliters of water to prepare a buffer solution for electrophoresis, what would be the best container for that? And if you look at the Erlenmeyer, you can see there's a 500 mil mark, and all these have 500 mils. The problem is Erlenmeyers or bottles or even beakers don't have a great deal of accuracy. So you actually would want to use the graduated cylinder, because you would pick, let's say, a 500 milliliter cylinder and fill it up to that mark, put the meniscus at that 500 mil mark. So these would give you approximate amounts, but they're not very accurate. So we kind of call it beaker accuracy or bottle accuracy. You really can't count on it, just because it isn't as good as having this thin column to look at to measure. When we measure mass, we use the top loading balance. So these are great for measuring out media and salts and things like that for solutions. If you want a really fine-tuned measurement where you're getting down to the milligram, then you have to go to an analytical balance that has the little doors on the side that restricts air currents. But for things that are in the gram or tenths of gram range, the top loading balance is just fine. You probably already know measuring temperature. We use thermometers. Most of the time, these are alcohol. Mercury has some toxicity, so a lot of times we just want to lower toxicity in case the thermometer breaks. But we measure in Celsius, so 0 being freezing and 100 being boiling then. pH is a measure of how much acid or base is in solution, and so we use pH meters, and we'll probably get a little bit of experiments with that later in the semester. So these are calibrated. You have a calibration procedure you go through with the specific buffers, and then you have your unknown that you test to measure the pH in. So really important in the lab when we work with bacterial cultures or other cultures is we many times want to have sterile materials. And when we sterilize, it means we've destroyed all the microbes. And that's really hard to do unless you have the right equipment. So usually we use an autoclave. And so this is very similar to the one we have in our prep area. This other picture is a larger autoclave. There's varying sizes, but you would take your solutions or media and load those in and then process them for 15, it's usually 15 minutes at 15 pounds per square inch. And that gives the steam, then the temperature is 121 degrees centigrade. And if we're there at 15 minutes, we will kill all bacteria, viruses, fungi, everything is sterilized in that length of time. But you need that autoclave. You can actually do the same thing with a pressure cooker. So if you processed it in a pressure cooker for that long, you could do the same thing. Disinfection, though, is kind of just our routine cleaning, and that gets rid of most organisms. So we could disinfect with a bleach solution or alcohol. I mean, you could certainly kill bacteria that way, but to be sure that everything's killed, you've got to use the autoclave. So UV light's good for surfaces, even microwaving, but again, it's limited, and you can't count on actually sterilizing. So a little bit about numerical data. I don't want to go too much into detail, but you've probably already experienced a little bit of significant figures. So when we write a number down, it's based on the material that, the instrument that I'm using to measure, or the material that I have to work with in terms of how accurate I can measure that. So significant figures says that the number of figures number of digits to the right, so the first non-zero number to the right of the decimal point is a significant figure. So if you look at these numbers, 0.003, 0.002, and 0.01 all have one significant figure. And so that was something, I think when I first heard that, it kind of wasn't obvious to me, but that's just one of those rules of significant figures. And then when we add or subtract or multiply, we base our final calculation on the fewest number of significant figures that's present. So for instance, if I have 21.3 and I subtract 0.232 grams, when I do that measurement or the calculation, so if I subtract that, I get 21.068. And at that point, I have 5 significant figures, but my original numbers only had 3 significant figures. So I want to have my final answer. So if it's 21.068, I would round up to 21.1 because I want that number of significant figures to be the same as the least number in my original starting calculation. And the same thing when multiplying and dividing, you follow that same rule. So I have a calculation here where I have 30.5, which has 3 significant figures, 2.223, which has 4 significant figures. And then when I write 5.00, that would actually have 3 significant figures because I put those 2 zeros after that. So when I do that calculation, I get 15.5603. But again, I want to have 3 significant because that's the least number I have. I can't put more than that. So I'm going to round that to 13.6. So don't stress on this if this is new to you. It's something we'll work on in lab, and we'll work through plenty of examples of that. The units of measure, of course, everything in science is based on the metric system. And so you are probably familiar with kilograms and milligrams, probably maybe not have heard of decigrams and centigrams, but these are orders of magnitude relative to the gram and so forth. So if I look at the kind of measurements we're going to use in our lab, we're really working in the milli range, so milliliters, then microliters, and then nanometers. Probably won't get that point, but I'll talk about nanograms or nanomoles when we're talking about measuring DNA and so forth. So it's not something we can measure, but we can calculate that. But we can definitely measure milliliters and microliters. So these are the ones I want you to focus on. So it's 1,000th of a gram or 1,000th of a liter. And then micro is a millionth or 10 to the minus 6. And if you haven't done scientific notation for a while, I'm going to have a worksheet on that to help you kind of review that. So solutions, we do a lot of measuring or diluting. And so it's important to have different ways to calculate those and show what we're talking about here. So percent solutions is either mass per volume or volume per volume. So for instance, if I was going to make normal saline is 0.9%. So I would have as 0.9 grams per 100 milliliters. So that calculation is 0.9 per 100 times 100. So that gives me my 0.9% there. And I could do the same thing with measuring volumes. And just a reminder, the solute is the material that you're dissolving or adding to the water. And usually my solution then is water plus something else. So the water itself is the solvent. So the solute is the chemical that I'm adding. So in this case, it'd be sodium chloride. Molarity refers to the mole, and mole, of course, refers to Avogadro's number, and you find out the mass of a mole by looking at the atomic weight or formula weight. So one example, we're going to talk about calcium chloride. We're going to use that in one of our experiments later on. And if you look at the molecular weight of calcium and chlorine and multiply the chlorine molecular weight by 2 and add the calcium, you get 110.98. So to make a 1 molar solution, what I would have is this many grams, 110.98 grams, and I would dissolve that in 1 liter of water, and that would give me then a 1 molar solution. So again, if this is new, if something I haven't talked about for a while, don't worry, we don't stress on it right now. It's something we're going to introduce later on. I do want you to learn this right now because it's something we're going to work with this week, and that's just making basic dilutions. So if we have known concentrations, we can then use it to dilute to make concentrations that we desire. So concentration 1 times volume 1 equals concentration 2 times volume 2, and that's how you set up your ratio and proportion. So a lot of times we have these what we call X concentrated. So 1X is like our working stock. And so 50X is 50 times concentrated. So if I have a 50 times concentrated buffer, so TAE stands for tris acetate EDTA. It's a common buffer we use with DNA. So what would you need if you wanted to make a 1X solution, but just 150 milliliters? So simple calculation, how much 50X do you need? So I know I have 50X to start with, and what I want is 1X, 150 mils of that. So my desired concentration and my volume here. So I want a 1X and volume of 150 milliliters. So if I set that up, 1X times 150, and then I would divide by 50, I then get 3 milliliters. And the way you can kind of check yourself with that is just plug this back in. If I multiply 3 times 50, I get 150. And over here, 150 times 1 is 150. So you can always check yourself to make sure you did that calculation right. So I would take that 3 milliliters, and then I would put it probably in a graduated cylinder and bring that up then to a total of 150 milliliters. You would not, for instance, want to take 150 mils and add 3, because now you're at 153 and now you're not at the right concentration. So you take this and you add the water or the solvent to that. So quick run through of chapter 2. A lot of this is going to make a lot more sense when we start doing it in lab, but I want you to, for the exam study guide, is to go back through chapter 2 and just review what is the BSL level of our lab, what PPE do we wear, what personal protective equipment do we need to wear in the biotech lab, what's the difference between sterilization and disinfection, what are the key components of a laboratory notebook, so that list that was on the previous slide. And what do these acronyms represent? So the safety data sheets, what are the BSL levels, what does HEPA stand for? And then I'm going to put some pictures in the quiz. And so you need to identify the Erlenmeyer versus reagent bottle versus the micropipettes, pipette pump, and so forth. So I think it shouldn't be too difficult. Couple other things that we just talked about is you need to be able to do this calculation, C1 V1 equals C2 V2. And if you go to your textbook, there's some more examples of that. And then know these units of measure that we work with in lab. So that'll conclude this section. And if you do have questions, make sure that you ask those questions in lab this week and before you do take that exam. So I'll be seeing you in a couple days in lab.